Geometric Physics 1, Lecture 8, Cotangent Bundles, Lifts, and Generating Functions. Today's reading is Marsden and Ratiu, sections 6.1 through 6.5. For next time, read sections 6.6 and 6.7 on magnetic terms, together with the Poincaré lemma. Lecture 3 showed you the tautological one form and asked you to trust it. Today we proved that it deserves its name. Lecture 7 gave us the abstract object. A symplectic manifold carries a closed non-degenerate two-form omega. Darboux's theorem then told us that locally there is nothing more to know. Today we study the one family of examples that physics actually hands us. On a cotangent bundle, the canonical coordinates are not a local accident. They are global and they are natural. They all descend from a single one-form theta with omega equal to minus d theta. The route has 4 stops. First, the linear model, where t star v is v cross v star. Second, theta on t star q, defined intrinsically, and the tautological property that names it. Third, cotangent lifts. A diffeomorphism of q preserves theta exactly, and therefore preserves omega. Fourth, lifted group actions and generating functions. Here is what to carry through the hour. Lecture 3 wrote theta equals p I d q I on the board. Today we earn it. Theta is not a formula in coordinates. Theta is the only one form on t star q that could exist without making a choice. First, the linear case. We do everything on a vector space and its dual where there is no geometry to get in the way. Let V be a finite dimensional real vector space. A vector space is its own tangent space at every point. So t star v is just v cross v star. And the tangent space to v cross v star at any point is again v cross v star. Now the canonical one form. A point is a vector w together with a covector alpha. A tangent vector there is a pair, a vector u together with a covector beta. Define capital theta at that point, applied to u and beta, to be the pairing of alpha with u. Look at what capital theta throws away. It throws away the base point w. It throws away the covector part of the tangent vector. All that survives is the pairing of the covector you are standing on with the vector part of where you are going. The canonical two form is capital omega defined as minus d of capital theta. Written out, it is the pairing of the second covector with the first vector, minus the pairing of the first covector with the second vector. Capital omega is bilinear. Capital omega is antisymmetric. And capital omega does not depend on the base point at all. Choose a basis for v and a dual basis for v star. That gives induced coordinates on v cross v star, and we call them q upper I and p sub I. In those coordinates, capital theta is pi dqi and capital omega is dqi wedge dpi. As a matrix, it is the familiar block form built from the identity. Capital omega is non-degenerate, and the proof is 2 lines. Suppose capital omega vanishes with u and beta in the first slot. Test against a tangent vector with nothing in the vector slot. That forces the pairing of every covector with u to vanish, so u is 0. Test against one with nothing in the covector slot, and beta is 0 as well. Closeness is cheaper still. Capital omega is minus d capital theta, so capital omega is exact, and d capital omega vanishes. Now the sentence to keep. This is precisely the model space in Darboux's theorem. What differs is where the structure comes from. Darboux hands you canonical coordinates locally and only after a change of chart. Here they are present from the start, because a vector space and its dual come with a pairing and nothing else. Now the nonlinear case. We replace the vector space by a manifold, and the striking thing is how little changes. Here is the definition, and it is forced on us. We stand at a point of t star q. That point is a covector alpha q sitting over a point q of q. We are handed a tangent vector v there, and we want a number. We already own a covector. We are standing on 1. But alpha q eats vectors on q, and v lives upstairs. So push v down with the tangent of the projection, then feed the result to alpha q. That is the whole definition. Theta at alpha q applied to v is the pairing of alpha q with t pi of v. 2 consequences follow. Theta annihilates every vertical vector, meaning every vector in the kernel of T pi. Sliding along a fiber changes the covector, but not the point, and theta cannot see it. And the only ingredients were the projection and the duality pairing. No metric, no connection, no chart. So here's the sentence to keep. There is exactly one thing you can do with a covector at Q and a vector sitting over Q, and theta is it. That is why theta lives on every cotangent bundle and on no other manifold. Now put it in coordinates. Take a chart on Q and the induced chart upstairs. Write a tangent vector as a I times the partial by Qi plus Bi times the partial by Pi. Projection forgets the momentum components. So T pi of V is a I times the partial with respect to Qi, and theta of V is Pi Ai. In other words, theta equals Pi dQi exactly as promised in lecture 3. And omega is dQi wedge dPi. So T star Q with omega is a symplectic manifold, and every induced chart is already a Darboux chart. Closeness is automatic, because d omega is minus d of d theta, and d of d is 0. Non-degeneracy is the linear computation applied inside the chart. One remark, omega wedged with itself is a volume form, so T star Q is orientable whatever Q is. Now the sentence to keep. On a general symplectic manifold, d omega equals 0 is a hypothesis you impose. On T star Q, it is a theorem because omega is exact. Exactness is the extra structure a cotangent bundle has, and the rest of the lecture lists what it buys you. Why the word tautological? A one-form beta on Q is the same thing as a map from Q up into T star Q, whose composition with the projection is the identity. Such a map is a section, and we may pull theta back along it. The proposition is this. For every one-form beta on Q, the pullback of theta by beta is beta itself. The proof is 4 lines. Take a point Q and a tangent vector u there. By the definition of pullback, we evaluate theta at beta of Q on the push forward of u. By the definition of theta, that is the pairing of beta of Q with T pi of the push forward. Now use the chain rule. T pi after T beta is the tangent of pi after beta, and pi after beta is the identity. So everything collapses to the pairing of beta of Q with u, which is beta on u. Now the sentence to keep. Every one form on Q is its own pullback under itself. Theta is the universal one form, one object upstairs that reproduces every one form downstairs at once. That is the tautology, and that is where the name comes from. Uniqueness is the other half, and it earns theta the definite article. Suppose some other one form upstairs, call it theta prime, also returns beta whenever you pull it back by beta. We claim it is theta. Work in an induced chart and write theta prime as AIDQI plus B upper ID PI. Step 1 uses constant sections. Fix a constant covector C and let beta send Q to the pair Q and C. The pullback of dPi is then 0. So the pullback of theta prime is AI times dQi, and the hypothesis forces AI to equal Ci. Since C was arbitrary, AI is Pi throughout the chart. Step 2 uses tilted sections where the covector varies with the point. Now the pullback of dPi is no longer 0. Matching against beta, everything cancels except a term carrying B. Tilting one coordinate at a time forces every B to vanish. So theta prime is PIDQI. The two steps are the two directions upstairs. Step 1 pins theta prime down where sections can point. Step 2 kills it on the vertical where no section can. Now the payoff. We take maps of the configuration space upstairs, and we watch what they do to theta. Let F be a diffeomorphism of Q. The cotangent lift of F is the pointwise dual of the tangent of F. In detail, T star F takes a covector at the image point and returns a covector at Q. Its pairing with U is the pairing of the original covector with Tf of U. So T star F carries the cotangent space at the image point back to the one at Q. It covers F inverse rather than F. Here is a convention warning. T star is contravariant because covectors pull back. So the lift of a composition reverses the order, and the lift covering F in the same direction is the cotangent lift of F inverse. both maps preserve theta. Different books call either one the lift, so fix your convention before comparing formulas. In coordinates, the lift is easy. Write q tilde for f of q. The lift sends the pair q and p to the pair q tilde and p tilde. And p tilde sub I is the partial of q upper j by q tilde upper I times p sub j. You have seen that formula. It is the covariant law for momentum from lecture 3. Now read as the formula for a map. Now the theorem, and it is the center of the lecture. For every diffeomorphism f of q, the cotangent lift pulls theta back to theta itself. Consequently, it pulls omega back to omega. Write capital F for the lift, and recall that pi after capital F is F inverse after pi. Take a covector alpha q and a tangent vector v there. The pullback of theta on v is theta at capital F of alpha q on the push forward of v. By the definition of theta, that is capital F of alpha q paired with t pi of that push forward. Now apply the defining property of capital F to the vector tf inverse of t pi of v. For that u, the push forward tf of u is exactly t pi of v. So the pairing collapses to alpha q paired with t pi of v, which is theta on v. Preserving omega is then automatic, because pullback commutes with d. Here is the same proof in coordinates. Tilde I dq tilde I equals pj times the partial of qj by q tilde I times dq tilde I, and that is pj dqj. The corollary is the reason this lecture exists. The cotangent lift of f is a symplectomorphism. So Hamilton's equations, written as the interior product of xh with omega equals dh, keep their form in the new variables. Think about what you were spared. Verified by hand, canonical means checking a long list of Poisson bracket relations. New positions must have vanishing brackets with each other, so must new momenta. A new position against a new momentum must give the Kronecker delta. Each identity is a sum of two n terms built from derivatives of f and of f inverse. The theorem replaces all of it with one composition rule and the chain rule. Examples are everywhere: rigid body coordinates, normal mode coordinates, elliptic coordinates for the two-center problem, body frame against space frame. Every one is a point transformation, so every one is canonical. Now the sentence to keep. Changing configuration coordinates can never break Hamiltonian structure. The reason is that you do not get to choose how the momenta transform. Once the positions move, the momenta are dragged along by duality, and theta is the bookkeeping that makes the drag automatic. Two lifts computed. First, polar coordinates on the punctured plane. Take x equal to r cosine phi and y equal to r sine phi. The lift hands us the new momenta at once. Sub r is cosine phi times px plus sine phi times py, and p sub phi simplifies to xpy minus ypx. That last expression is the angular momentum. And by the theorem, px dx plus py dy equals pr dr plus p phi d phi. Nobody had to guess the momentum conjugate to an angle. The lift produced it. Second, a linear map on Rn, take f of q equal to aq for an invertible matrix A. The lift sends q and p to aq, together with A inverse transpose p. If A is a rotation, then A inverse transpose is A itself. Momenta rotate exactly like positions, which is why elementary mechanics never distinguishes the two. Now the sentence to keep. Angular momentum was not postulated here. It appeared as the angular component of theta, which is to say, as a coordinate of the phase space we already had. Lecture 19 turns that into the momentum map. Which canonical transformations are lifts? Define the Liouville vector field z equal to pi times the partial by pi. The flow of z scales each fiber and leaves the base point alone. A short computation gives two identities. The interior product of z with omega is minus theta, and the lead derivative of theta along z is theta. So z is determined by theta and omega together, and z vanishes on the zero section. Now the theorem, a diffeomorphism capital F upstairs preserves theta if and only if it is the cotangent lift of a diffeomorphism of Q. One direction we just proved. For the other, preserving theta forces preserving omega, hence preserving z. Preserving z means commuting with fiber-wise scaling. So capital F fixes the zero section and is linear on each fiber. Its restriction downstairs is the diffeomorphism we wanted. Now the sentence to keep. Two conditions, and one is strictly stronger. Preserving omega is being canonical. Preserving theta is being a point transformation. All of classical transformation theory lives in the gap between them. The gap is measured by theta minus the pullback of theta, which is closed but need not vanish. Generating functions are what you get when you integrate it. Now let a group act. Let capital G act on Q by diffeomorphisms, and write capital phi sub G for the diffeomorphism attached to a group element G. The cotangent lifted action is defined as the cotangent lift of capital phi sub G inverse. The inverse looks fussy, and there is a reason for it. The proposition has three parts. The lifted action really is an action of capital G upstairs. It covers the original action, meaning that projecting after acting is the same as acting after projecting, and every lifted map preserves theta, hence omega. The first part is contravariance. The cotangent lift of a composition reverses order, and the inverse in the definition reverses it back. The other two parts are the theorem on lifts, applied one group element at a time. An action like this is called exact symplectic. It preserves not merely omega, but the potential theta that omega came from. That extra word is worth a great deal. Now the sentence to keep. A symmetry of the configuration space is automatically a symmetry of the phase space, and nothing needs to be checked. That is why almost every symmetry group in mechanics is introduced as a group acting on the configuration space. Because a lifted action preserves theta, a conserved quantity comes with it for free. Take a Lie algebra element, xi, and let xi sub q be its infinitesimal generator on the configuration space. Define capital J by the following rule. The pairing of capital J at alpha q with xi is the pairing of alpha q with xi sub q at q. Equivalently, capital J is theta evaluated on the generator upstairs. No integration and no case analysis. One pairing. The examples are ones you already know. Take R3 with the translation group. The lifted action shifts Q and leaves P alone, and capital J is the linear momentum. Take instead the rotation group SO3. The lifted action rotates both Q and P, and capital J is Q cross P. That last check is one line. The generator at Q is Xi cross Q. So the pairing of capital J with Xi is P dotted with Xi cross Q, which is Xi dotted with Q cross P. Now the sentence to keep. Noether's theorem on a cotangent bundle is not a computation. It is an evaluation of theta. Lecture 19 proves that this capital J is equivariant and Poisson, and Lecture 20 uses it to reduce. Last stop, generating functions, which are what canonical transformations look like when they fail to be point transformations. Let capital F be a canonical transformation, so the pullback of omega is omega. Look at the one form theta minus the pullback of theta and take its exterior derivative. Since omega is minus d theta, the answer is minus omega plus the pullback of omega. That is 0, so the one form is closed. Closed is not exact in general, but on a contractible region, the Poincaré lemma, proved in Lecture 9, upgrades closed to exact. So the difference is d capital S, and capital S is the generating function. Classically, the same statement reads PIDQI minus P tilde I dq tilde I equals d capital S. The opposite sign is also common, so fix it once and stay with it. There is a geometric version. Capital F is canonical exactly when its graph is a Lagrangian submanifold of two copies of T star Q, and a Lagrangian submanifold projecting nicely to the base is the image of d capital S. Now the sentence to keep. A canonical transformation moves two n variables, yet one function of n variables encodes it. That compression is why generating functions exist. A cotangent lift is the case where d capital S is 0. Capital S is a function of n old variables and n new ones. For each conjugate pair, you keep either the position or the momentum. That gives 4 choices, and hence the 4 classical types. Type 1 uses the old and new positions. Type 2 uses the old positions and the new momenta. Type 3 uses the old momenta and the new positions. Type 4 uses both momenta. In every case, the remaining variables are recovered as partial derivatives of the generating function, with a minus sign attached whenever a momentum is an argument. The 4 types are Legendre transforms of one another. Why 4? Because no single type covers every canonical transformation. The Legendre transform you need can be degenerate. The identity map, for instance, has no type 1 generating function at all, since for the identity the old and new positions are not independent variables. Geometrically, the 4 types are 4 coordinate charts on one Lagrangian submanifold. The degeneracies are exactly the places where a chart fails to be a chart. Learn the mechanism and not the table. 3 examples, and then the reason it matters. First, the identity. Take a type 2 generating function equal to q upper I times p tilde sub I. Differentiating returns the identity map. Second, the exchange. Take a type 1 generating function, q upper I times q tilde upper I. Now q tilde comes out equal to p and p tilde equal to minus q. Positions have become momenta. Nothing in omega distinguishes the two. Third, point transformations. Take a type 2 generating function equal to f of q contracted with p tilde. Differentiating gives q tilde equal to f of q and the covariant law for the momenta. That is the cotangent lift of f. So the lifts are the type 2 generating functions linear in the new momenta. Now Hamilton-Jacobi, let capital S depend on time and hunt for a transformation making the new Hamiltonian vanish. The requirement becomes one equation. H evaluated at q and at the derivative of capital S by q plus the derivative of capital S by time equals 0. Now the sentence to keep. Solving one first-order partial differential equation replaces integrating 2n ordinary differential equations. That trade is the Hamilton-Jacobi method, and Lecture 11 is about it. 6 things to carry away. 1. On a vector space crossed with its dual, both canonical forms come from the duality pairing and nothing else. That is the Darboux model here for free. 2. On a cotangent bundle, theta at alpha q applied to v is alpha q paired with t pi of v. Theta is intrinsic. Theta kills vertical vectors, and theta reads PIDQI in any induced chart. Then omega is closed because it is exact. 3. The pullback of theta by any one form beta is beta itself, and theta is the unique such one form. 4. Cotangent lifts preserve theta exactly, so every point transformation is canonical. Preserving theta characterizes the lifts. 5. A group acting on the configuration space lifts to an exact symplectic action upstairs, carrying the pairing of alpha q with the infinitesimal generator. That is the momentum map of Lecture 19. 6. Theta minus the pullback of theta is closed. Where it is exact, it is d capital S, a generating function. 4 types, 1 Lagrangian submanifold. For Lecture 9, read Marsden and Ratiu sections 6.6 and 6.7. Fibre translations and what happens when you add a closed but inexact 2 form. The result is symplectic but not exact, and it is a charged particle in a magnetic field.